So this video is the first of two videos all about scientific notation. And in this case, we're going to look at what scientific notation is, a little bit about what the definition is, how we write it, what qualifies as scientific notation, and converting from scientific notation to what we call standard form, which is the familiar type of number that we're used to seeing. The second video, after we've had a class on this, will be going from standard form back to scientific notation, but today we're going to really talk about what the basics of it is and do a little bit with converting from scientific notation to standard form. And to start talking about scientific notation, I'm going to ask you to look at this very, very large number that I have on the next slide here. This number is called a googol. And a googol, spelled G-O-O-G-O-L, not like Google the search engine. But to make a googol, you take a 1 and you add 100 zeros to the end of it. So 1 followed by 100 zeros. Now, if we had to write that out every time that we were talking about it, that would be a really, really long number. Even if you could write it at 1 0 a second, that's 100 seconds. Even if you get to 2 or 3 zeros a second, you're still looking at either 50 seconds or even 30 to 35 seconds, depending on how fast. So obviously, we don't want to spend that much time looking about it. Some numbers we give names to, like Google, but the idea of scientific notation is talking about very, very large numbers and very, very small numbers. So I'm going to ask you to do a quick calculation, a little bit of review of powers and exponents and what they mean. So I'm going to ask you to evaluate the following three expressions: 3.5 times 10 to the first, or 3.15 times 10 to the second, and 3.15 times 10 to the third. Go ahead, pause the video, work out those calculations, remember your order of operations, and come back when you're ready to move on. So the digits that you're talking about haven't changed. The three calculations you should have gotten were 31.5, 315, and 3,150. And so what you probably notice is that when we're multiplying by 10, we're not changing the digits. The digits stay in the same order. Instead, what we're doing is we're making the number larger and larger and larger. And as we go through and we add more powers of 10, the decimal point shifts. So going from 3.15, multiplying it by 10 once, your decimal point has shifted one place. Multiplying it by 10 twice, your decimal point has shifted 2 places. Multiplying it by 10 3 times, your decimal point has shifted a total of 3 places, and we needed to add a 0 because we ran out of digits in our original decimal number, and we can just keep adding zeros the more and more times that we multiply by 10. And the idea that we can take a number and multiply it by 10 a number of different times to create much larger values for numbers is really what's behind what's called scientific notation. And scientific notation is just a way of writing very large numbers, or very, very small numbers also, that saves time and it saves space and allows us to work with things that would be otherwise very prohibitive because of how large or how small they are. So I'm going to ask you to write down a few different things, and then we're going to go through what each piece of this means. First, talking about scientific notation, then this entire piece here, especially including that example there with the C in the end. Go ahead, pause the video, write that down. We'll talk about what it means, and then we'll come back when you're ready to move on. Okay, so scientific notation has a number of different pieces to it. Much like those calculations we just did, we have a number being multiplied by a power of 10. And the number that's being multiplied, this C here, which I'm going to circle in yellow, C must be greater than or equal to 1 and less than 10. So it's a number between 1 and 10. It is allowed to be 1, is not allowed to be 10. Essentially, it has to have a ones digit, and it can have as many decimal places after that as we would potentially want, but it cannot be greater than one whole number digit. So it can be 7.3, but it can't be 73. It could be 9.7, but it can't be 97. It could be 1.365, but it can't be 1,365. It can be 1, but it can't be 10. That's the most important part about C. And then N, which is our exponent here with 10, just has to be a whole number. Can't be a decimal, can't be a fraction, has to be a whole number. So scientific notation is made up of two pieces. One number C that's between 1 and 10, and an exponent for 10 that is a whole number. So we end up with something like 3.15 times 10 to the third. Now let's take a look at a few examples of scientific notation and how we convert them into what we call standard form. Standard form is how we're familiar with seeing numbers. And then we'll go on with a few problems for you to work on your own. Now if you feel like you have an understanding of how this works and you want to work out this calculation on your own, you can go ahead and do that. Otherwise, you can go ahead and watch this video. We're going to get a trick here for looking at how to convert from scientific notation to standard form, and then we'll go on to those practice problems. So the first one that we have all the way at the far left is 1.537 times 10 to the second. Now, this 10 to the second is times 100, and that's multiplying by 10 twice. Every time we multiply by 10, we move the decimal point one place. So if we're going to multiply it by 10 twice, the decimal point is going to move 2 places to eventually become 153.7. Now, if you multiply 1.537 times 100, you'll find that we get 153.7. So the fact that I didn't go through and actually do the multiplication doesn't affect the final product. Instead, we're using what we know about multiplying by 10, which is every time you multiply by 10, you move 1 decimal place, to shortcut the process and convert easily from scientific notation to what we call standard form. This form right here, 153.7, is called standard form. It's our standard place value. There are no exponents, there are no fractions, it's just decimal form. Now, we have the same number, 1.537 times 10 to the third. If we multiply by 10 3 times, we move our decimal point 1, 2, 3 places, which moves all the way to the end of the number, so we end up with 1,537 for 1.537 times 10 to the third. Again, start with the decimal point, move it that number of places. Now for 1.537 times 10 to the fourth, we need to move our decimal point 4 places, but we only have 3 digits, so we need to add a 0 to the end, and we get 15,370. And now if we move it 6 places for our last one, we have 3 places for the digits we see, and we need an extra 3 places. So we add an extra 3 zeros to get 1,537,000. So as you can see, scientific notation can start with the same decimal, and then based on the number that is your exponent for 10, we can represent a whole array of large numbers, and we can do that in a fairly condensed form. Now obviously writing 153.7 is not too bad, and so we may not need to write 1.53 times 10 to the second, but if we started having things times 10 to the 9th, to the 12th, to the 15th, to the 18th, talking about the distances between stars, the distances between planets, then having a way to write those very, very large numbers becomes really super helpful. So now here is 4 practice problems for you to work on. Remember, you move the decimal point according to the value in the exponent. Go ahead, pause the video, work on these problems, and come back when you're ready to move on. So in the upper left-hand corner, we have 3.96 times 10 to the third. That means we need to move the decimal point over 3 places. We have 1, 2, 3, so we need to add a 0 to it, and we end up with 3,960. For the second one, 7.021 times 10 to the first, we only need to move the decimal point 1 place. It becomes between the 0 and 2, so 70.21. For the third one down on the bottom, I'm going to write this one out because we have a lot of decimal places to move, 1, 2, 3, 4, and then 3 more, because we need a total of 7, so we have to add 3 zeros, and we end up with 10,073,000, 100,730,000. And then finally, 4.855 times 10 to the fourth. We have 3 places to move it. We need 1 more, so 48,550. So scientific notation has those 2 parts. We'll talk about it more in class. And we can use what we know about multiplying by 10 and shifting the decimal place to make the process of converting from scientific notation into standard decimal form easier as a way of representing very, very, very large numbers in a compact way that simplifies it as far as time and space for writing it.